Bismillahirrahmanirrahim. In this lecture, I am solving problem 6.46 from the book Fundamental of Thermodynamics by BORGNAKKE. So the statement of the problem is a small turbine shown in the figure. This is the figure of the turbine. This is a small turbine. Is operated at part load by throttling a 0.25 kg per second steam supplied at 1.4 megapascal and 250 degrees centigrade. There are three states. This is state 1, this is state 1, this is state 2, this is state 1, this is state 2, and this is state 3. So here at state number 1, P1 is equal to 1.4 megapascal, which is equal to 1400 kilopascal, and temperature T1 at this state temperature is equal to 250 degrees centigrade, down to 1.1 megapascal before enter the turbine. This state 2 is before entrance of the turbine. So before the entrance to a turbine, pressure P2 is equal to 1.1 megapascal, which is equal to 1100 kilopascal. This is the pressure before entrance to the turbine. And the exhaust mean exit after turbine point state 3. State 3 pressure is 10 kilopascal. So at state number 3 pressure P3 is equal to 10 kilopascal. So I am revising the statement. A small turbine shown in figure is operated as part load by throttling from 1 to 2. This process is throttling. This sign is for throttling. So it means that H1 is equal to H2. Throttling process is from 1 to 2. So H1 will be equal to H2 due to throttling. Process. And m dot, here m dot is equal to 0.25 kilogram per second. A steam supply, this is the supply of the steam at 1.4 megapascal and 250 degrees centigrade, down to 1.1 megapascal before it enters the turbine. Before the entrance of the turbine, pressure dropped to 1.1 megapascal, and exhaust is at 10. This is the exhaust P3, which is equal to 10 kilopascal. If the turbine produce 110 kilowatt, we know that turbine produce work output. So work output W dot, it is in kilowatt, so we will write W dot, which is equal to 110 kilowatt. Find the exhaust temperature and quality if saturated. Required is number 1, find the exhaust temperature T3. Exhaust of the turbine is state number 3, so at this point temperature is T3, and the quality X3. Find T3 and X3 if saturated. So first we will check at point 3 whether it is saturated. So if this is saturated, then we will find X3, quality of the steam or dryness fraction. So this is the given data. Now with the help of throttling process from 1 to 2, we can find enthalpy. If we find enthalpy at point 1 or at point 1 or at point 2, then at both stages, at both states, the enthalpy will be equal. So first we check whether point 1 is in saturated region or superheated region. So for state 1, in state 1 temperature is given to us as 250 degrees centigrade and pressure is given to us as 1400 kilopascal, 1.4 megapascal or 1400. So first we check whether point 1 is superheated region or saturated. So from saturated steam table at pressure P1 is equal to 1400 kilopascal. Find saturation temperature. So this is the pressure 1400 kilopascal. So at this pressure the saturation temperature is 195.07 degrees centigrade. 195.07, and the temperature given to us is more than this value, as T1 is 250 greater than T3, as T1 greater than Ts. So the temperature T1 is superheated temperature, and state 1 is in superheated region. So to find H1 we will use superheated steam table. So from superheated steam table, at temperature is equal to 250 degrees centigrade and pressure is equal to 1400 kilopascal. Find H1. So go to superheated steam table. This is superheated steam table, and here pressure is 1400 kilopascal and this temperature is 250. So this is the enthalpy. So in front of 250 and below 1400 kilopascal, enthalpy is 2927.22 2927.22 kilojoule per kg. And as H1 is equal to H2, we know that from the throttling process, so H1 is equal to H2 is equal to 2927.22 kilojoule per kilogram, because at state 1 and state 2 enthalpy is constant. Now we are finding H3 from the steady state equation. We apply steady state equation on the turbine, and this region from 2 to 3 we apply the steady state equation. So apply steady state equation on turbine. So steady state equation is Q dot minus W dot plus M dot H2 plus V inlet square divided by 2 plus GZ2 is equal to M dot H2 plus V exit square divided by 2 plus GZ3. So this is process is adiabatic. So Q dot is equal to 0. So W dot plus M dot H2 plus M dot Vi square V inlet square of the turbine divided by 2 plus GZ2 is equal to M dot H2 plus V exit square divided by 2 plus GZ3. Here potential energy change in potential energy is neglected, so these will be cancelled. Similarly, we assume inlet velocity and exit velocity uniform, so this will be neglected. So it means that W dot, this is H3, so W dot, this is minus W dot plus M dot H2 is equal to M dot H3, or we can write this as W dot is equal to M dot H2 minus H3, or we are finding H3 from this, so we can write this as, we are finding H3 with the help of this equation. So H3 W dot is equal to m dot H2 minus m dot H3, or m dot H3 is equal to m dot H2 minus W dot. These equations are same. These two equations are same. No need of this step. So so H3 is equal to m dot H2 divided by m dot minus W dot, or m dot will be cancelled. So H3 is equal to H2 minus W dot divided by m dot. Now put the values here. So H2 is equal to H1 and H2 are same. H2 is equal to 2927.22 kilojoule per kg, minus W dot is given to us as 110 kilowatt, and watt is equal to joule per second. M dot is given to us as 0.25 kilogram per second. So this second will be cancelled with second. So H3 is equal to 2927.22 kilojoule per kilogram minus 110 divided by 0.22 is equal to 0.25 is equal to 440 kilojoule per kilogram. So H3 is equal to 2487.22 kilojoule per kilogram. Now at the exit of the turbine, now we are finding exit temperature and quality at the exit of the turbine. So at the exit of the turbine, we know that P3 already given to us 10 kilopascal, and this is H3, which is equal to 2487.22 kilojoule. Now first we check whether this is saturated or not. So from saturated steam table, at pressure is equal to 10 kilopascal, find HF and Hg, because H3 is known to us. So from the saturated steam table, at pressure is equal to 10 kilopascal, this is pressure 10 kilopascal, and here this is HF and this is Hg. HF is equal to 191.81. HF is equal to 191.81 kilojoule per kilogram, and Hg is equal to 2584.63 kilojoule per kilogram, as H3 is equal to 2487.22 kilojoule per kg. This is greater than HF and less than Hg, between HF and Hg. So state 3 is saturated. State 3 is saturated. So temperature at state 3 is saturated temperature. So from saturated steam table, at pressure is equal to 10 kilopascal, P3 temperature T3, which is the required, is equal to saturation temperature, and this is equal to at 10 kilopascal, saturated temperature is 45.81 degrees centigrade. 45.81 degrees centigrade. Now we can find X3. So we know that H3 is equal to HF plus X3 Hg minus HF. Rearrange this equation. So X3 is equal to H3 minus HF divided by Hg minus HF. So H3 is equal to 2487.22 minus H1 is 191.81 divided by Hg is 2584.63 minus 191.81 and unit is kilojoule per kg, and here kilojoule per kg. So simplify this and find the value of x3, which is equal to 0.959, and this is the end of the problem. And for more problems, please like and subscribe my YouTube channel and share with your friends. Thank you.